Okay, so right on the topic, force equilibrium. Just a minute. Okay, so what is force equilibrium? Equilibrium in physics refers to a state where all the forces and torques acting on the object are balanced, causing the object to remain at rest or continue moving at a constant velocity. So you can recall Newton's first law. What is Newton's first law says? Unless an external unbalanced force is applied, the object remains at rest, the objects which are stationary remains at rest, and object in motion remains in constant velocity. Okay. So equilibrium means the state of an object, whether either it is at rest or moving at constant velocity. So these things we can achieve only if there is no any unbalanced force. That means the forces has to be balanced. Now, for example, if I take this object placed on my hand, now it's stationary because it is balanced and influence of two forces. So here this one is balance, influence of two forces. Those two forces are its weight acting vertically downwards towards the earth and the normal reaction force acting vertically upward. So they are equal and opposite. So they are cancel each other. So the resultant force will be zero, right? So if an object is in equilibrium, the first condition is the resultant should be zero. Okay, the resultant must be zero. If an object is in equilibrium, the first thing is the resultant must be zero. Okay. And the second thing is the moment of force must be zero. So these are the two things that is required to check whether object is equilibrium or not. Okay. Right. So when an object is equilibrium, it is either stationary, remains at rest, or moves at constant velocity. Okay, so that one, that which is explained by Newton's first law, right? Unless an external unbalanced force is applied, the object at rest remains stationary and object in motion remains constant velocity. Okay, so you can write the definition for equilibrium. So equilibrium in physics refers to a state where all forces and torques, so forces and torques acting on an object are balanced. So forces and torques acting on object are balanced. So that means the resultant force must be zero and the net torque also must be zero. So these two should satisfy in order to achieve a equilibrium state. Okay. So you can write this down. So this equilibrium session, we can finish it off by today. Hopefully, yeah. Okay. And then types of equilibrium. There are two main types of equilibrium. One is static equilibrium and dynamic equilibrium. So static equilibrium means the object remains stationary. It's not moving, static. It is stationary. Dynamic equilibrium is achieved. The velocity is constant. Okay. So static equilibrium, the object is at rest. Example, a book lying on a table. Okay. And dynamic equilibrium, the object is moving with constant velocity. So zero acceleration. So zero acceleration is dynamic equilibrium. Yes. Example, a car moving at constant speed on a straight road. A car moving at a constant speed on a straight road. So when a car moves at constant speed, the driving force that is given out by the engine rotates the wheel and the wheel pushes the road backward, so there will be a forward friction force that will be the driving force actually. So this driving force will be equal to the drag force. So drag force like friction, and also because you have studied in two-wheel drive, like for example, the engine is connected to only to the back wheels, then only the back wheels will push the ground backwards, right? So then the front two wheels slide, so there will be a friction force. It is actually a opposing force, so it is a resistive force. Okay, and also the air resistance. So the drag force will be there, air resistance and the friction. Okay, so those are drag forces. Excuse me guys, give me a second. All right, okay, I'll return next time to that site. Okay, so when a car is moving at constant speed, the driving force will be equal to the drag forces. Therefore resultant force will be zero. It will move at constant speed. Okay, so therefore there are two equilibrium types, or the states of equilibrium. There are two states of equilibrium. One is static equilibrium, where the object remains stationary, and then dynamic equilibrium, where the object moves at constant velocity. Okay. Okay, so then we'll see the conditions for the equilibrium. So already I told you there are two conditions for the equilibrium. One is the resultant force has to be zero, and the second thing is the torque, net torque must be zero. Okay, to achieve equilibrium, two key conditions must be satisfied. Okay, two conditions must be satisfied. Uh, you can take down notes while I'm explaining. If in case you couldn't write down, means totally fine, because I will share this PDF in the group so that you can complete your notes. Anything apart from the note, if I say something, you can note down in your writing book. Okay. All right. So the conditions for equilibrium. To achieve equilibrium, key conditions must be satisfied. So the first condition is the resultant force must be zero. That means to achieve a translational equilibrium. That means translational. Now, what is the meaning of translational motion? Does anyone know what is the meaning of translational motion? So if I ask you what is translational motion, how can you give an answer? Translational motion. Kinetic motion, no, it somewhat okay, but it doesn't explain thoroughly. Because if you consider the rotational motion also, it is kinetic. It has some kinetic energy, right? Translation motion, constant acceleration. No, because even with non-uniform acceleration, there could be a translational motion, because the particle move, like accelerates and then again decelerates and then stops, and then acceleration is 2 meters per second squared and then 5 meters per second squared acceleration. So still the particle is moving, so it's a translation motion. Okay, the translation motion you can define like this. If the center of mass of an object, the position of the center of mass of an object, very good. There is a displacement of center of mass, very good. So the translation motion is there will be a displacement or change in displacement of the center of mass of the object. Then we call it as translation motion. But if you consider the rotation motion, if object is rotating, its center of mass doesn't change. It will remains. Now, for example, if I take this and if I rotate, okay, this will rotate. I mean, if I rotate freely, it will rotate about the center of mass. So then if it's only purely rotation, means the center of mass uh, position does not change. It won't change. But if it has a translation motion also, that means while it is rotating, it moves. Then there will be a movement in the center of mass. Okay, so the translation motion you write as the displacement. There will be a change in displacement in center of mass. Change in displacement. So these things now you can write down in your notebook because it's not there here. Change in displacement of the center of mass of the body. Center of mass of the body or object. Okay. So that is translation motion. So rotation motion, we can define every particle will move in a circular, every particle will move in a circular path, but no change in the position of the center of mass. That is rotation motion. Now rotation motion and things we will learn in our within couple of probably next week, because we have to, after this equilibrium, we have to start work, energy and power. So after that we have rotation motion, and then after rotation motion, circular motion and hydrostatistics and fluid dynamics. With that we can finish the mechanics. Okay, so translational equilibrium. Okay, to achieve a translational equilibrium, the resultant force must be zero. So the resultant force must be balanced. The resultant should be resultant vector should be a null vector. Okay, the resultant vector should be a null vector. That means the magnitude is zero. Okay, the vector sum of all forces acting on the object must be zero. Now, if for example the resultant, if you so let's say this is the resultant. So you can think a resultant in is the resultant of two perpendicular components, right? Fx and fy. Okay, fx, fy. So let's say this is r. So we know r, the magnitude of the resultant is equals to fx squared plus fy squared squared. So in order to achieve r equals 0, according to mathematics, both fx and fy must be equal to 0, right? Now, in vectors, you studied like system of coplanar forces, how to find the resultant of system of coplanar forces. Then we resolve into vertical, horizontal component and vertical component, and then we take horizontal components separately, and then vertical components separately. So when we do that, the resultant, the horizontal component, fx, this fx, that is total horizontal component should be 0, and also y also must be 0. Okay, or in other words we can say simply the resultant r must be equal to 0. To achieve translational equilibrium, r must be equal to 0. Okay, so that is the first condition to achieve equilibrium. Okay, so there is another case now. For example, let's say there is an object. Okay, here I apply a force, let's say 10 Newton, and there's this pivot point. In this side, I apply 10 Newton. Okay, so then this one, if you consider the resultant is 0. Okay, resultant is 0, but there is a clockwise non-zero movement. So that is a movement of force couple. So the movement of force couple, we know how to find. It will be given by one of the force multiplied by the distance between them, perpendicular distance between them. Let's say that is x. So 10 into x. So therefore there will be non-zero movement. So therefore it will, what happens? It will accelerate in now initially, let's say it's stationary, but if I apply force both sides, what happens? It starts rotating. So initially it is not rotating, but it is now start to rotate, that means angular displacement is changing, therefore angular acceleration will be there. So that angular acceleration achieved by this non-zero moment of force. Okay. So moment of force, we know it is referred as torque. Okay. Okay. To achieve rotational equilibrium, the moment of force must be zero. Okay. So therefore, if our object is in equilibrium, means its resultant must be zero, and the torque in counterclockwise or anticlockwise must be zero. Okay. So those are the two conditions for equilibrium. Okay. So you can write this down. Okay, the vector sum of all force acting on the object must be zero. That means the resultant should be zero. So you can write R should be equal to. So here I am writing the vector. Then I can't write this is equal to zero because vector cannot be equal to scalar. If I am writing in the vector notation, I should write the null vector. Okay. Or else you can write the magnitude of the resultant. Then the magnitude is equal to zero. That is okay. Understood. So here they have written 0 means they are writing the magnitude. The magnitude of the resultant in the horizontal direction should be 0. Magnitude of the resultant in the vertical direction should be 0. Okay. Now, for example, 3 into AB vector. You take AB vector multiplied by 3 vector multiplied by scalar. You get another vector which is pointing in the same direction, 3AB vector. Like then if I take 0 multiplied by AB, if I write 0, it's wrong. Okay. By the way, this is not there in our syllabus. You don't have to worry. Just to give you some idea about what is vectors means. So vector multiplied by a scalar, you will get another vector. So you get null vector only. If you are writing, if you are true mathematician, you will write like this. Okay. Okay. Anyway, that's some additional thing. All right. Okay. So the resultant is equal to 0. This ensures that the object is not accelerating in any direction, or we can say no uh, movement of center of mass. No movement of center of mass. Center of mass of the object. No movement. So the center of mass point won't change. Okay. And the rotational equilibrium, the torque should be balanced. The sum of all torques about any axis. So it is about any axis. Okay, that's something you have to highlight. About any axis must be 0. Okay. So this ensures that the object is not rotating or it rotates at constant angular velocity. So it is equilibrium in rotational equilibrium. Okay, if the torque is equal to 0. All right. Yeah, linear motion is another terminology for translational motion. Now, by the way, linear motion and translational motion has a difference. Linear motion, also referred as rectilinear motion, straight line motion. They all means that acceleration is constant. Acceleration is constant. So that is linear motion. Okay. So all the linear motions are translational motions, but all the translation motions are not linear motions. Okay. All the translation motions are not linear. Okay, now say now you are going to do solve problems considering like there is a object which is in equilibrium. Now you are supposed to find the normal reaction force or the tension acting on the, now let's say something is hanging from a spring. So you want to find the tension. The first thing you have to do is you have to mark the free body diagram accurately. Okay. So you have to identify the object of interest, represent it as point or space, simple shape. So okay, you can note down later, but it's not so important. But you have to draw free body diagram. I hope you already know how to draw free body diagram. Okay, and then solving equilibrium problems. Okay, so if you want to solve, we have to consider these two cases. The resultant should be 0 and the torque also must be 0. Okay, now let's move on. Let's do some questions. Okay. Now, for example, let's say there is object. Let's say there is object, and let's say this side some force, and here is a force. Here's a force. Okay. So let's say this 20 Newton, and this is X, and this is 50 Newton. So let's start from a simple questions. This is very easy. You might think why I'm giving such question. Kela. Let's start from 0. Okay. So here find the value of X. Find the value of X if the object is in equilibrium. If the object is in equilibrium. Okay, so what is the value of X? Any response, please text to the TKI. Simply to left. Okay. Okay, so the answer is 70 Newton. Okay. So now let's move on to another type of question. Okay, so let's say there's a boy of mass 50 kilogram. Yeah, and the Planck mass is, let's say, Planck has mass of 30 kilogram. Okay, and here an object let's say mass is 40 kilogram. Okay. The Planck is uniform. Planck is uniform and yeah, has a mass of 30 kilogram. Okay. So if the system is equilibrium, you need to find two things. One is this normal reaction force, and also the distance to this to the center of gravity of this object from point, let's say O. I take this point O. Okay, so do you want me to give the question in words? Do you want to write the question in words? What about Zufar and Abhishani? Okay. So here you need to find the normal reaction force acting at this support, and also the distance to the let's say this to the object or block, to the block from the point O. Okay, I'll give you a couple of minutes to try this question. If you got the answer, means you can share. The Planck is uniform and has a mass of 30 kilogram. Okay, I got an answer from Hirosh. Okay. So here x is measured from the point O. Okay. Okay. I got some answers. Let's see whether they is correct. Okay. So first thing is in equilibrium questions, the first thing is you have to mark the forces. Okay. So here R will be there. So the weight of the boy here acts vertically downward. So the weight of the boy acts vertically downward, and therefore now I'll consider the forces acting on the plank. Okay. So if you consider the boy here, I'll explain. So let's say I draw the boy, enlarged figure. Okay. So his weight vertically downwards mg, and here the normal reaction force S will be there. So if you consider the equilibrium of this boy, the SC equals mg. So therefore SC equals mass is 500, so 500 Newton. Mass is 50, so 500 Newton will be this. So therefore, if you consider this the Planck, so equal and opposite reaction force will be acting on the Planck S according to Newton's third law. So that S will be equals to 500 Newton. Now this is the actual way of getting this, but when you are dealing with this, you will know that you won't be marking all of this, but straight away you can write here. This is here the force will be 500 Newton. So writing these and all not necessary, even in the essay question. But if they are particularly asked, can write the free body diagram of the boy and show that this normal reaction force will be 500, then you have to do. Okay. Apart from that, now relevant to this particular question, no need to mark this and all. You should be able to understand. Okay. So here, therefore, here there will be a normal reaction force. The boy pushes because of the boy's weight, his leg pushes the plank downward with a force of 100 Newton. And similarly, here to this weight, here it will be downward 400 Newton. And the plank for a uniform rod, like plank, its center of gravity will be at the midpoint. So total length is 8 meter. Therefore, somewhere here, 1 meter from O, the weight of the plank will act downward. So it's 300 Newton. Therefore, it is sorry, its mass is 30 kilograms. So therefore, it is 300 Newton. And those are the vertical forces acting on the plank. Okay. And also this normal reaction force. Then I can consider the vertical force equilibrium. So if I consider the vertical force equilibrium, considering the vertical force equilibrium, we can see only the forces are minus 500 minus 300, because I'm considering vertically upward. So you have to indicate the direction also. Minus 500, 300, minus 400. So these are the all forces acting on the plank. So if it's equilibrium, the resultant should be 0. So therefore, R is equals to 900 and 300, 1200 Newton. So therefore, the normal reaction force here will be 1200 Newton. Okay, and the next thing is I want to find this distance x. So therefore, I'm going to consider the torque You can consider the clockwise torque or anti-clockwise torque. I consider the clockwise torque because the weight of this makes clockwise torque. So therefore I take clockwise torque. So therefore 400 into x, 400 into x plus this is also the weight of the plank also making a clockwise torque. So 300 into 1, and then this one, the boy's weight, it makes, due to the boy's weight, this force will be anti-clockwise. So minus 500 into 2 equals, the net torque has to be 0, then only it will be in rotational equilibrium. So then we can simplify here. 400 into x equals 500 into 2000, 1000 minus 300. So therefore x equals 700 divided by 400. Am I right? So 400 into x plus 300 into 1 minus 500 into 2. So 700 over 400. So these 2 cancel, 7 over 4. You can get what is 7 divided by 4? 1 is 4, remains 3. For 37, 28 remains 2, 1.75. 4 into 5, 20. Okay. So therefore x equals 1.75 meters. Okay. Is this clear? Abhishani, did you understand? Because I didn't see any message come from you. Three hundred into 1. Yes. Hold on. So 2 plus 6, 8. So 8 divided by 2, 4. Therefore here it has to be 2 meter. Yes, 300 into 2. Okay, so, okay. Thank you for that. Okay, so here 300 into 2 should be there. So 1000 minus 600. Yes. So 1000 minus 600, because the length of the plank is 8 meter and the center of gravity will be its midpoint, meaning that 4 meters both sides. Therefore, he already 2 meters means this length has to be 2 meter. So 1000 minus 600, 400 divided by 400. So it nicely comes 1 meter. Okay then, so your answers are correct. Okay. So now here you don't need to mark forces acting on this boy or here its weight, all no need. You have to mark only the forces acting on the plank. Okay, right. So we'll move on to the second question. You can take a screenshot if you want. Okay. Okay, so here's the two springs. Okay, two springs, and then a plank which is 6 meter long, and a buoy of mass 40 kilogram stands at the edge of this plank. The plank has plank mass is let's say 20 kilogram, and length is 6 meter. So it's a uniform plank. Okay. So let's say this point is A and here B. So here there will be tension. Yeah. So the question is, find the force acting on the spring. Yeah, hold on. Find the magnitude and the direction. Okay. I take this spring as A and this is B. So the question is, find the magnitude and the direction of the forces acting on spring A and spring B by the plank. Okay, so that's the question. You have to find the magnitude and the direction of the force acting on spring A and spring B by the plank. Anyone got the answer? You need more time, or shall I start the discussion? All right, so I start here. So the first thing what we had to do, we had to mark the free body diagram. So I'm going to mark the free body diagram of this plant. So that's the first thing you should do. So we can see there is a downward force here due to the weight of the boy. The leg pushes the plant downward with the force of 400 Newton. So that force is equal to the weight of the boy. Okay, and then the plank has a mass of 20 kilograms, so its weight acts vertically downward from its center of mass. So it will be somewhere here, 200 Newton. So this length is 1 meter. because the Planck is total 6 meter. So the midpoint will be 3 meter, right? So 2 plus 1 or 4 minus 1. So here will be the center of gravity. The Planck, so it's weight x from here. And then I can mark the forces acting on this spring. So here and here, okay. So I take this as R1 and this is R2. Okay. So then first I can consider the vertical equilibrium. So if I consider the vertical equilibrium, considering vertical equilibrium, so I can write R1 plus R2 is okay, minus, so minus 200 minus 400 is equal to 0. So this one you can write, you can take this minus term to the other side, right? So straight away you can write R1 plus R2 is equals to 200 plus 400, right? So upward force is equals to downward forces. So 200 plus 400. So therefore R1 plus R2 equals how much? 600. This is equation 1. Okay. So then we have two unknown variables. Therefore, we need to obtain another equation to solve the system, to solve this problem. Okay. So therefore, what I can do is I can take a moment about this point or this point. So you can take any point. So let's say I'm taking from this point. Let's say O. So taking moment, I consider clockwise movement from this end, from point O. Then I have this 400 Newton making clockwise. So 400 into the distance to that is 4 meter. And this R2, now we are taking the movement from the line of action of R2. So therefore R2 won't come, right? Because we know if you take the movement from the along the line of action of a force, so then the perpendicular distance will be 0. So therefore R2 will not come into this equation. So then we have again R1 is clockwise, R1 times the distance is 2 meter. So this is should equals to 0. The net moment must be equal to 0 to maintain equilibrium. So then we have, I write the unit fast. Okay, so I have 2R1 equals minus 1600. Therefore, R1 equals minus 800 Newton. So this is, we get minus means the R1 is actually in the downward direction. So we can write this in the downward direction. So R1 is in the downward direction. Okay. And then now using equation 1, I can find R2. So R1 is equals to minus 800 plus R2 equals 600. Therefore, R2 is equals to 600 plus 800. Yeah. Therefore, R2 equals 1400 Newton. Okay. So here you can see in downward we have these forces. This 400, 200, 600, R1 also downward 800. So totally 1400. That 1400 should balance by this R2, 1400 Newton. Okay, right. So therefore, we can write the answer for this question. So we want to write the magnitude and the direction of the spring, the force acting on spring A and B. So I can write spring A uh, downward 1400 Newton, and spring B upward, sorry, spring A is 800, spring R1 is 800 Newton, and this is 1400 Newton, which means that spring A is under compression. This spring experience a compression force. Hold on. Yeah. So this one experience a compression force, and this experience I think I made a mistake somewhere. Okay. So here I have to take the weight of this. Yes. All right. I will start from the beginning. Okay. So considering the vertical equilibrium, we have this equation R1 plus R2 equals R1 plus R2 equals 600 Newton. Okay. Okay. So here, okay, so here R1. Okay. So R1 plus R2 is 600 Newton, that's the equation 1. And then I'm taking the moment from 0.0. Okay, so then we have 400 into the distance is 4 meter plus the weight of the plank is 200 into the distance is 1, and then R2 will not come, and minus and plus R1 into the distance 4 meter into 4, this should equals to 0. Okay. Yeah, we can't take R2 because we are taking the moment from the line of action of R2. So the perpendicular distance will be 0, right? So therefore it won't come. We did this in moment of force, right? So it won't make a moment about that point O. So 400 into 4 is 1600 plus 200 is equals to 4 times R1 equals to 0. So 4R1 equals minus 1800. So R1 is equals to minus 450 Newton. So R1 is minus 450 Newton. Yeah, 2R1, the distance is 2 meter. Sorry guys. Bad. Okay. R1 into 2 because the distance is from here, its length is 2 meter. So 2R1 equals 0. Therefore, 2R1 equals minus 1800. So therefore, R1 equals minus 900 Newton. Okay. R1 is equals to minus 900 Newton. R1 equals minus 900 Newton. Okay. So therefore, the R1 is actually acting downward. Okay. Right. So here, then we can find R2. So R2, R1 is minus 900 plus R2 equals 600 Newton. Therefore, R2 equals 1500 Newton. Okay, 200 and here 400, 600 and 900. R2 equals 1500 Newton. Okay, so these are the forces that I have found acting on the Planck. Okay, so then I can draw this figure again. Just I'll draw the Planck and the spring. So here the Planck and so here's the Planck and the spring. And the boy is here. Okay. No need to draw those things and all. So the weight, due to the weight of the boy, this will be pulled downward with force of 400 Newton. And its weight will be here 200 Newton. So the weight of the boy and weight of the Planck tries to push this Planck downwards. So therefore what happens? Now let's say, imagine this. Here if I push here downward, what happens? This side will tends to move up. No, now this is a rigid body, right? This is a rigid body, and if I push a force, if I apply a force, this end tends to move up. To avoid that, the spring will hold this, right? The spring is pulling downward. Spring is pulling downward. So therefore the force actually here will be downward, R1 will be downward. So that's why you got R1 is negative. So it's here downward here. The magnitude is R1 900 Newton. And here on the Planck, it will be 1500 Newton. Okay. So now this is the free body diagram. The same thing I have marked here. Now in this question, we want to write the forces acting on the spring by the Planck. So first I consider the spring A. Spring A. Now the spring A pushes the Planck downward with the force of 900 Newton. Therefore, Planck pushes the spring upward with the force of 900 Newton. Therefore, the force on the spring by the Planck will be upward 900 Newton. Raise your hand if you understand this. Raise your hand, did you understand this? How this is physically possible? Which one you are referring? Spring A. So the question is find the magnitude and the direction of the forces acting on spring A and B by the Planck. Now here this force 900 we have marked what it is, the force acting on the Planck by the spring, because here in this free body diagram we have marked only the force acting on the Planck. These forces are acting on the Planck. So according to Newton's third law, equal and opposite reaction force will be there on the spring. So now when this buoy and its weight pushes this downward, this end uh, tends to move this direction. So, but due to the spring, it holds that. That means the spring at this end pushes downward. Okay. So therefore, the force acting on the plank will be downward. Therefore, equal and opposite reaction force acting on the spring, A upward. Mm, into at the beginning it's 400 into 4, I mean here. Okay, so here I'm considering the clockwise movement. So from this point, so this one also, this one, the weight of the buoy is 400, it is also clockwise. This one also clockwise, and this one also clockwise. So all plus there. But if you know already, like this force will be downward, then if you mark that is downward, then in that case, then you can take minus R1 into 2. Okay. But here I have marked the force. I don't know. Actually, I know. I assume I don't know. So I have marked this upward. So when we do the calculation, we found that is minus, meaning that it will be downward. Okay. Okay. So spring A, the force acting on spring A is upward 900 Newton. Spring B is downward. So there will be tension force. I mean, there will be force acting on the plank by the spring, 1500 Newton. Therefore, force acting on the spring by the plank will be 1500 Newton downward. Okay. So therefore, the spring A is under spring A is under tension, and then spring B is under compression. So here tension, and this is compression. So spring A is under tension, and spring B is under compression. Okay. Any question about this question? I think one of the similar type of question being asked in past paper for mechanics, something 2006, 7, something I'm not sure. But there was a mechanics past paper question, something similar to this. So they have actually combined this force equilibrium and the rotation motion. So it is about some diver diving to the swim. So when he's dive, he bends his body and rotation motion will be there. So both combined together. Some past paper question is there. Okay. Any question regarding this? Did you understand? Okay. Abhushan, is it clear for you? Okay. I think one more. So here we get support, and we have a string, and then rot. One meter, and this is 3 meter, and here this mass is m, and this is hold on. This. Okay. So when I take 4 kilogram. So these are connecting wires. Connecting wires are light. Okay, so this is a rigid support, and these are the masses. So there are 4 masses are there, and these green color ones are connecting wires, metal wires, but they are light compared to the mass of these objects. The connecting wires are light. Okay. So here you want to find this x value, and let's say this is 4 meter. This is 2 meter. Kilogram, 3 kilograms. Let's say this is equal. So here this length and this length equal, something like both, I can say 2 meter, 2 meter. Okay. So here you need to find this length x and mass m. Okay. Find m comma x. Yeah, I make this 2 kilogram. Yeah. Mm, no, it's wrong. It's actually a easy question. If you do this type of question once, it will be really easy. Okay, so here we can consider the if it's equilibrium, we can consider the moment. The net torque has to be 0. So if I start from here, if I get the moment from here, x into 2 should equals to 1 into m. But both are unknown, so I can't consider start from here. So here it's correct. 2 into 3. Now from this moment, this equilibrium. 2 into 3, and here also 2 into 3, so it's in equilibrium. So then the first thing we had to take the moment from this point. I take the moment from point O in clockwise direction. So 4 into, so here the tension, okay, acting downward. So that will actually carries this total mass 2 plus m. So 4 into 2 plus m, 2 plus m into g, because distance times the force. Force is here, okay, here 2 plus m into g, okay, minus this here, it has an anti-clockwise movement, 2 into total mass is 6. So 6 into g equals 0. Now here you might be wondering how I take here this force is 2 plus m into g. So for that, what you can do is here you can consider this object and consider the force equilibrium. Here the tension T upward, weight here 20, which is 2 into G, 2 into G, and here also it is M into G. So if you consider the vertical equilibrium of this part, then you get T equals upward force equals to downward force. 2 plus 2G plus mg, so which is 2 plus m into G. Okay, is that clear? Okay. If you have any question, let me know. Okay. So therefore, here we can cancel G and G. So we have 4 into 2 plus m equals 2 into 6, 12. Minus 12 goes to the side, plus 12. So 2 plus m equals 12 into 4, 3. Sorry, 12 divided by 4 is 3. Therefore, m equals 1. So m equals 1 kilogram. Okay, so actually to do this question, no need to write these things and all. You can see clearly. From here, if you take the moment, the weight, the force acting downward from this point is 60. Okay, 60 Newton. Okay, so when you're taking the moment both side, G cancels. So therefore you can consider the mass also. So 2 into 6. So 2 into 6 equals 4 into how much? 2 into 6 is 12. So here 4 into which number? If you multiply, you get 12. We know the factors of 12 are 2, 3, 4. So here 4 means here this mass, total mass should be 3. So here 2 kilogram. Therefore this one has to be 1 kilogram. So here this 2 kilograms, so this for m is 1 kilogram. So you can get it without even repeating. So here you can see 2 into, so here total mass is 6, 2 into 6, 12. So this side movement also should be 12. So 4, therefore this mass, total mass has to be 3. So 4 into 3 is 12. Then therefore 12 and 12 balance. The movement will balance. So therefore total mass has to be 3. So therefore 2, here it will be 1. Right? And then since you know this is 1, here 1 into 1 should be equals to x into 2. So therefore x has to be half. 1 into 1 equals x into 2. Therefore x equals half. So x equals half meter. Is that clear, everyone? Hirosh and Bhushani. Okay. So you can find more questions from past papers and all. If I also try to send, I think that paper which I shared for center of gravity, it has equilibrium also, I think. Anyway, I send more questions from equilibrium. All right. So then the force equilibrium, the object is in equilibrium under the influence of three forces. Okay. So when an object is subject to three forces and it is in equilibrium, the vector sum of these three forces must be zero. So one thing, the vector sum must be zero, and also the moment, the net torque, moment of force must be zero, and also there is another thing which we will study, that all three forces, if an object is equilibrium under three forces, all three forces line of action intersect at a common point. Okay. Here this means that forces balance each other and the object remains rest or moves at constant velocity. Okay. So the conditions for equilibrium with three forces. So again, it's same. For in order to achieve translation equilibrium, the resultant must be zero. and then rotational equilibrium. To achieve rotational equilibrium, the torque must be 0. And additionally, for 3 non-parallel forces to balance. Okay, so if you have 3 parallel forces to be balanced, so for example like this, which is your first example, today's first example, you wrote 3 parallel forces. Okay, so here let's say here 10 Newton and this 20 Newton. Therefore, in order to achieve equilibrium, this force has to be 30 Newton. So these are parallel forces. Okay, and here now we are going to discuss about non-parallel. Okay. Okay, so for 3 non-parallel forces, to balance, they must be concurrent. That is, they meet at a single point or they must lie in a single plane. Actually, you should write up to here. Okay, because in fact, in our syllabus, we study only about forces in coplanar forces, right? We don't discuss 3D forces and all. So therefore, you had to write this condition for equilibrium with 3 forces. So the first one, the translation equilibrium should achieve. That means the resultant has to be 0. So the conditions you can write, the first condition is resultant has to be 0. Resultant should be 0. And the second one, torque should be 0. Meet a single, the line of action of 3 forces. The line of action of the 3 forces goes through a common point. So these are the conditions for now. If this first and second achieve means that is already in equilibrium. Okay, but this third point we can use to do more calculation in a very easy analytical way. Okay. Collinear. Yeah, I heard that word collinear. Wait, I'll check. Collinear is a frequently used term. Not suddenly getting for this meaning. Collinear means 3 points lying on the same line. Okay. Yeah, collinear 3 points are lying in the same line. Sorry, same line. The collinear term widely used in this coordinate geometry. No, it's concurrent is different. Concurrent means they must be, okay, I'll explain you that. So the line of action of the 3 forces, yeah, 3 forces go through a common point. So my grammar, sorry for my grammar here. three forces plural, so it has to be go. The line of action of the three forces go through a common point. So that means now let's say object is equilibrium under three forces. Okay, I'll explain you with an example. So an example, let's say inclined plane and object is placed on it. Okay, I'll ask you a simple question. Can I keep this object in equilibrium on a smooth plane? Okay, how about Zufar and Abhushani? Okay, good. Abhushani? Can I keep an object in equilibrium on a smooth inclined plane? Okay, so we can't. The answer is no, right? So here its weight acts vertically downward from the center of gravity. So mg, and then the plane has to be rough. So the friction will be there. Friction will be here in this direction because this tends to move downward. Therefore, friction will be acts in this direction. Friction. So therefore, tell me if I draw the normal reaction force like this. Is it correct? Okay. My drawing, is it correct? Yes or no? Quickly put, each of you should drop a message in the chat box. Hirosh, your answer is wrong. So Hirosh says this one should go through the center of gravity. That also reasonable. No? Okay. Anyway, first tell me, the question is I have kept here. So this one is correct or wrong? So how many of you say it's correct? If it's correct, say yes. If not, no. Please, each of you text to the TKI, so then I can comparatively see easily from here. Okay, I got 2 yes and 1 no. Okay, so here this is wrong. Okay, this is wrong. Okay, then the second question. Now, if I draw the normal reaction force here, now tell me, is this correct or wrong? Again, each of you has to say your answers. I got the answer from Abhushani and Sufar. Okay, so here this one also wrong. The correct one should be, I'll draw the correct one. So correct one is from here. Okay, because when this object is equilibrium under the influence of three forces, normal reaction force, okay, R, mg, F. So it's equilibrium under the influence of three forces. Then here we have the third one, the line of action of the three forces go through a common point. So they all should go through this common point. So therefore normal reaction force will be here. Okay. Is that clear? Did you understand? Okay. So here the object is in equilibrium under the influence of three forces. Therefore, all three forces should go through a common point. Okay, another example. Okay, I'll take. Another example. Okay, so here. It is not three forces are intersecting. So it is the line of action of the three forces. Okay. So the line of action of the three forces should go through the common point. Okay. Because now, for example, if you have object like this, so one is applying force this direction, and someone applying force this direction, and someone applying a force this direction. Okay. So then line of action only will go through the same, right? So the line of action of each force should go through the common point. So if it's in equilibrium, okay. And here definitely here the friction is acting from this point. Oops. The friction force is actually acting from this point. Okay. Because if you find the resultant of the friction and the normal reaction force, it will be equal and opposite to the tension, the weight. So this will be the resultant of F and R. So it will now you know how to find the resultant of two perpendicular forces. So based on this F and R value, depending on their value, the magnitude will change. So if it's in equilibrium, then definitely the resultant will be uh, exactly opposite to the mg. So the magnitude of this, let's say I take as S vector. So S is the sum of R vector plus F vector. Then S magnitude will be equals to mg. Okay. If it's in equilibrium. Okay. By the way, I didn't get another example. By the way, when you are doing questions, you can find out more. Okay. Okay. So the other thing is if three forces F1, F2, F3 act on an object and are equilibrium, then they can be represented as a side of a closed triangle of forces. This means that if we arrange the three forces vector tail to head, they will form a closed triangle. Okay. If three forces are in equilibrium, they can be represented in magnitude and direction by the side of a triangle taken in order. So this one you should write. So we call this force equilibrium triangle. Bala samatulitata trikoni. Force equilibrium triangle. Force equilibrium triangle. So if three forces, if an object is balanced under the influence of three forces, for example, we can take our previous example where weight is acting downward, R is this direction. Yeah. So for example, here if you take, let's say here R is friction and then the weight acts downward. So then we can take these three forces as let's say this F1, this F2, and this F3. So to more generalized case, I take from here. Then what you can do is you can form a triangle. Okay. So what I do is okay, let's see whether if we have something like these three forces, F1 and F3, are they equilibrium or not? What you can do is you can take this each and see whether you can form a triangle. No. So therefore, according to polygon law of vector addition, according to the polygon law of vector addition, the resultant is given by this. So there will be resultant. So according to this diagram, this is not in equilibrium. So if it's equilibrium, we can make a triangle. So this does not make a triangle. Therefore, there is a non-balance. So there will be a resultant force, unbalanced resultant force. Okay. So let's consider equilibrium equation. So I take three forces. One. Okay. So now let's say these are F1, F2, F3. So if an object is balanced under the influence of these three forces, then we can make a triangle. Let's see, is it forming a triangle? No. So to form a triangle, this side has to be little bit, the magnitude of this has to be little bit higher so that it will form a triangle. So therefore, then this object will in equilibrium. You can consider with the triangle of vector addition. So you have studied triangle of vector addition. Okay. By the way, so after writing this, you can write this. Oh yeah. So you can illustrate this. So one is this one is this. So the resultant is equals to null vector. Because you can think of using triangle of vector addition. According to triangle of vector addition, the resultant of f1 and f2. So if you take the only f1 and f2, its resultant is given by the third side of the triangle, which will be in this direction. Okay, the resultant will be here. The resultant of f1 and f2 will be this. So you can find this orange color, which I have marked as F. Let's say so. F is the resultant of F1 vector plus F2 vector. The addition of F1 and F2 is F. So you can see this F is equal and opposite to the F3, so they are cancel each other. So that will the resultant will be 0. Overall resultant will be 0. Okay, so you can write down that. So therefore the sum of F1 plus F2 plus F3, the resultant is 0, null vector. Okay, quickly note down after writing this. This is also referred as triangle law about force equilibrium. බල සමතුලිතතා පිළිබඳ ත්‍රිකෝණ ප්‍රමේය. Give me a second. Okay. Yeah, so these conditions for non-parallel forces. Okay. Guys, give me a couple of minutes. I'll be back soon. Okay. Okay. So the last part of today's discussion, Lami's theorem. Okay. So right on the topic, Lami's theorem. Okay, so here the Lami's theorem says when an object is in equilibrium under the influence of three forces, we can write this equation. So where F1 over sine alpha is equals to F2 over sine beta is equals to F3 over sine gamma. So here alpha, beta, gamma are the angles between the three forces. So I can indicate here. Here this will be alpha, this will be beta and gamma. Okay. So this is the Lami's theorem. So this is actually in combined maths also you will study as sine niyama, sine law. In combined maths you have trigonometry, cos law and sine law. So this is actually the sine law because we know the magnitude are directly proportional to the length. So therefore here f1 over sine alpha is equals to f2 over sine beta is equals to f3 over sine gamma. Here f1, f2, f3 are the magnitudes of the three forces. Alpha, beta, gamma are the angles opposite to the each respective force. Okay. Yeah, I think I have marked the angle 8. Yeah, the angle should be, hold on, after drawing the triangle. Sine, no, sine. Okay, so write down this equation and then you can draw this again f1, f2, f3. Mm. Okay guys, I'm a bit confused about here the angle. I think either angle will be here alpha, beta, gamma, or else it has to be alpha is the angle opposite to the f1, like the alpha, and f beta opposite to f2, beta and gamma. So either one of that will be okay. Thank you for sharing it. Yes. Okay. A over sine alpha. Yes. So that one is correct. Yeah. Thank you. So you can note down this. Yeah. So alpha is the angle, this angle. Like in my picture, in my drawing, you can see the alpha will be this one. Okay. So not this. Okay. So with this, we can conclude the session for today. So the time is sharp 11. So we will do questions based on this. I will find out some questions and share it in the group based on this equilibrium. So in equilibrium, most of the time you will get questions either from like previous one or this type. Okay. By the way, any questions from today's discussion? Okay then. So take care, study well. Good night. Bye.